You're standing on the observation deck of a spacecraft, 2.9 billion kilometers from home. Through the reinforced window, Uranus hangs in the absolute darkness of deep space, a pale blue-green sphere, serene and almost featureless. No swirling storms like Jupiter, no magnificent rings like Saturn, just smooth, quiet, almost inviting. You've been traveling for 13 years to reach this moment. 13 years of artificial light, recycled air, the same faces, the same walls. And now, finally, here it is. The ice giant, the seventh planet, the edge of the classical solar system. Your hand rests against the cold glass. You can feel the faint vibration of the ship's life support systems. You can hear the soft hum of electronics behind you. You can smell the metallic tang of filtered air. And you're about to descend into that calm blue atmosphere. What you don't know yet is that you're looking at one of the most hostile environments in the solar system. A world where the very laws of physics conspire to kill you in ways Earth never prepared you for. And once you commit to going down there, there's no coming back. From this distance, Uranus doesn't look dangerous. It looks almost peaceful. A distant marble, for times wider than Earth, rotating slowly in the void. Its pale cyan color comes from methane in the upper atmosphere, absorbing red light and reflecting back that ghostly blue-green. It's 50,724 kilometers across, massive enough to hold 63 Earths inside it. But compared to Jupiter or Saturn, it seems restrained, subdued. The surface gravity is only 8.69 meters per second squared, just 89% of what you feel on Earth. You could almost walk there if there was a surface to walk on. But that gentleness is a lie. Because Uranus isn't just tilted, it's rolled completely on its side. Its axis of rotation is tilted 98 degrees from the plane of its orbit. Imagine Earth lying down, with the North Pole pointing directly at the Sun for half the year, then the South Pole for the other half. That's Uranus. All the time. It takes 84 Earth years to complete one orbit, which means each pole experiences 42 years of continuous sunlight, followed by 42 years of absolute darkness. Right now, as you approach, the northern hemisphere is in its summer. The pole is facing the sun. But summer here doesn't mean warmth. It means the faint, distant light of a sun that appears 400 times dimmer than it does from Earth. And in 21 years, that hemisphere will begin its descent into a 4-decade night. On January 24th, 1986, Voyager 2 became the first and only spacecraft to visit Uranus. It spent just 6 hours in the planet's vicinity. 6 hours, after a journey of 8.5 years. But in those 6 hours, it returned data that fundamentally changed our understanding of ice giants. Voyager discovered that Uranus has a magnetic field, but not like Earth's. Not like any planet we'd encountered before. Earth's magnetic field is aligned roughly with its rotation axis. The North Magnetic Pole is near the geographic North Pole. It makes sense. It's predictable. Uranus's magnetic field is tilted 59 degrees from its rotation axis. And it's offset. The magnetic center isn't at the planet's core. It's shifted about 1/3 of the way toward the surface. Which means the magnetic poles don't stay in one place. As Uranus rotates every 17 hours and 14 minutes, the entire magnetic field wobbles and tumbles like a broken gyroscope. Voyager also measured the temperature. The upper atmosphere, at the 1 bar pressure level, where atmospheric pressure equals Earth sea level, is -224 degrees Celsius, 49 Kelvin, cold enough to freeze nitrogen solid. And it measured wind speeds at the equator, up to 900 kilometers per hour. That's 560 miles per hour, faster than the fastest Category 5 hurricane ever recorded on Earth. Winds tearing through an atmosphere so cold that methane condenses into ice crystals and falls as snow. But Voyager couldn't stay. It had to keep moving, out toward Neptune, and eventually into interstellar space. And for nearly 4 decades, Uranus remained mostly a mystery. Let's say you're descending now. Your spacecraft has released a probe, a reinforced capsule designed to survive the journey down through the atmosphere. You're strapped inside, instruments surrounding you, heat shields glowing as you punch through the upper layers. At first, it's almost gentle. The thin hydrogen-helium atmosphere barely slows you down. You can see the stars through the small viewport, fading as the atmosphere thickens around you. Then the shaking starts. You're at the 1 bar level now, equivalent pressure to Earth's surface. Temperature, minus 224 degrees Celsius. Your instruments are screaming warnings. The methane in the atmosphere is freezing, forming ice clouds that batter against your heat shield. But you keep falling. At 2 bars of pressure, the temperature has only risen to minus 210 degrees Celsius. The hydrogen around you is getting denser. The shaking intensifies. At 10 bars, you're at minus 170 degrees Celsius. The viewport has frosted over. You can't see anything now except the data readouts. Pressure climbing, temperature climbing, but not fast enough. At 100 bars of pressure, about 100 times Earth's atmospheric pressure, you're at minus 120 degrees Celsius. The hydrogen is behaving strangely now. It's not quite a gas anymore, not quite a liquid. It's in a supercritical state, where the distinction between gas and liquid stops making sense. Your capsule is groaning. The pressure is compressing the hull. You can hear metal creaking. At 1,000 bars, the temperature has finally climbed above 0 Celsius. But the pressure is crushing. 1,000 times Earth's surface pressure. The hydrogen around you is now a liquid, but not like water. It's under so much pressure that it's becoming metallic, conductive. The hydrogen atoms are so compressed that their electrons are stripped away, forming an ocean of liquid metallic hydrogen. Your instruments fail. The viewport implodes. The hull collapses. And you're still 10,000 kilometers from the core. But let's say, somehow, your capsule holds. Let's say it's made of some miracle material that can withstand the pressure. Let's say you survive the descent and you're now floating in the deep interior of Uranus. You're surrounded by darkness, absolute darkness. No light penetrates down here. The temperature is around 5,000 Kelvin, hotter than the surface of the sun. But you can't see the glow because the pressure is so intense that thermal radiation is absorbed within centimeters. The ocean around you isn't water. It's a bizarre mixture of water, methane, and ammonia, all superheated and compressed into an ionic fluid. A hot, dense, electrically conductive slush that makes up most of Uranus's mass. And somewhere below you, maybe 20,000 kilometers down, is the core. A rocky icy heart, perhaps 0.5 Earth masses, crushed under pressures we can't replicate in any laboratory on Earth. You try to move, but movement doesn't mean anything here. There's no up or down, just pressure, heat, and darkness. And then you remember, you've been descending for hours. Hours. And back on the observation deck, your crew hasn't heard from you. They can't. Your radio signal died when the pressure crushed your transmitter. Even if it hadn't, radio waves don't travel well through metallic hydrogen. You are alone. Completely, irrevocably alone. But the atmosphere is just the first way Uranus kills you. The second is its magnetic field. Remember, tilted 59 degrees from the rotation axis, offset from the center, wobbling every 17 hours. On Earth, the magnetic field protects us from solar wind, charged particles streaming from the sun. The field deflects them, channeling them toward the poles, where they create auroras. Uranus's magnetic field does the opposite. Because it's tilted and offset, the field lines don't form a neat, protective bubble. Instead, they twist and spiral in chaotic patterns. Some field lines connect directly to the solar wind. Others loop back on themselves. The entire magnetosphere, the region of space dominated by the planet's magnetic field, is asymmetric, unstable, wobbling as the planet rotates. Which means radiation belts don't stay in one place. On Earth, we have the Van Allen belts, regions of trapped high-energy particles held by the magnetic field. They're dangerous, but they're predictable. We know where they are. On Uranus, the radiation belts migrate. They move across the planet's surface as the magnetic field wobbles. Sometimes they're near the equator. Sometimes they're at the poles. Sometimes they're skewed toward one hemisphere. In February 2026, NASA's James Webb Space Telescope mapped Uranus's upper atmosphere for the first time in vertical detail. The NIR SPEC instrument observed the planet for nearly a full rotation, detecting the faint infrared glow from molecules high above the clouds. What it found was unsettling. Temperatures in the ionosphere, the region 3,000 to 4,000 kilometers above the cloud tops, where the atmosphere becomes ionized and interacts with the magnetic field, peaked at 426 Kelvin, about 153 degrees Celsius. That's hot. Much hotter than the frigid minus 224 degrees Celsius at the cloud level. The atmosphere is heated from above by energy from a magnetosphere and solar wind. But here's the disturbing part. The heating isn't uniform. The temperature and ion density vary dramatically with longitude. As Uranus rotates, different parts of the atmosphere heat up and cool down, driven by the wobbling magnetic field. Webb detected auroras, glowing curtains of light, like Earth's northern lights. But these auroras don't stay at the poles. They migrate across the entire planet, following the tilted, offset magnetic field as it tumbles. Paola Taranti from Northumbria University, who led the study, put it simply, this is the first time we've been able to see Uranus's upper atmosphere in 3 dimensions. With Webb sensitivity, we can trace how energy moves upward through the planet's atmosphere and even see the influence of its lopsided magnetic field. If you were in orbit around Uranus, you'd be bathed in radiation. Unpredictable, migrating radiation. One moment, you're in a relatively safe zone. The next, as the planet rotates, a radiation belt swings through your position. Your spacecraft's shielding was designed for steady, predictable exposure. Not this. Within days, your electronics start failing. Within weeks, you're experiencing acute radiation sickness. Within months, assuming you survive that long, cancer. And here's where it gets truly existential. You're 2.9 billion kilometers from Earth. Light, traveling at 300,000 kilometers per second, takes 2 hours and 40 minutes to cross that distance. Which means if you send a distress signal right now, we're in trouble. We need help. It will take 2 hours and 40 minutes to reach Earth. And Earth's response, assuming they drop everything and answer immediately, will take another 2 hours and 40 minutes to reach you. That's 5 hours and 20 minutes for a round-trip conversation. But realistically, it's not just a conversation. It's a rescue mission. And no rescue mission can reach you in time. The fastest spacecraft humanity has ever built, the Parker Solar Probe, can reach speeds of 163 kilometers per second when diving toward the sun. But that's using the sun's gravity. Out here, in the cold depths of the outer solar system, there's no such boost. Voyager 2 took 8.5 years to reach Uranus using gravity assists from Jupiter and Saturn. A direct trajectory, without those assists, would take even longer. Decades. By the time help could arrive, you'd be long dead. From radiation, from life support failure, from starvation, from madness. You are In every meaningful sense, unreachable. The solar system has a border, an invisible line beyond which rescue is not possible, where the tyranny of distance overrides every technological capability we possess. And Uranus sits right on that line. Webb's 2026 data revealed something else, something that deepens the mystery. Uranus's upper atmosphere is still cooling. In the early 1990s, ground-based telescopes measured stratospheric temperatures around 470 Kelvin. By 2014, Spitzer Space Telescope observations showed cooling to around 450 Kelvin. And now, Webb's measurements show 426 Kelvin. The planet is losing heat. Slowly, steadily, over decades. Why? We don't know. One hypothesis: Uranus's extreme axial tilt disrupts atmospheric circulation in ways we don't understand. Energy absorbed during the 42-year summer isn't retained. It radiates away into space faster than the planet can absorb new energy. Another hypothesis: something deep inside the planet, in that hot, pressurized ocean of water methane ammonia slush, is changing. Some convection pattern is shifting. Some heat transport mechanism is weakening. But we don't know. We can't know. Not from 2.9 billion kilometers away. Not with a spacecraft that flew by once in 1986 and never returned. Webb also confirmed something Voyager hinted at, but couldn't prove. Uranus has the coldest planetary atmosphere in the solar system. Colder than Neptune, even though Neptune is farther from the Sun. Why? Again, we don't know. Neptune radiates 2.6 times more energy than it receives from the Sun. Internal heat, left over from its formation 4.6 billion years ago, still leaks out into space. Uranus radiates almost exactly the energy it receives from the Sun. No excess. No internal heat. As if the planet's core is inert, frozen, dead. But that doesn't make sense. A planet doesn't just lose its internal heat. Not on these timescales. Not completely. Unless something happened. Some event, early in Uranus's history, that stripped away its primordial heat. The leading theory: billions of years ago, Uranus was struck by an Earth-sized object. The impact was so violent, it knocked the planet onto its side. And it ejected enough material, enough of the hot interior, that Uranus lost most of its internal heat in one catastrophic moment. But that's just a theory. We have no proof. No way to test it. Not yet. In 2022, the National Academy's Planetary Science and Astrobiology Decadal Survey released its priorities for NASA's next decade of exploration. At the top of the list, Uranus. Specifically, a mission called the Uranus Orbiter and Probe, UOP. The mission concept is ambitious. A flagship-class spacecraft, launched on a SpaceX Falcon Heavy, would fly to Jupiter for a gravity assist, then cruise outward to Uranus. Total travel time, 13.4 years. Upon arrival, it would insert itself into orbit, the first spacecraft ever to orbit an ice giant. It would deploy an atmospheric probe, descending into the clouds to measure composition, temperature, pressure, wind speeds. Everything Voyager couldn't measure in its brief flyby. Then, over 4.5 years, the orbiter would conduct multiple flybys of Uranus's 5 major moons: Miranda, Ariel, Umbriel, Titania, Oberon, each a world unto itself. Some show signs of past geological activity. Titania has massive canyons cutting across its surface. Miranda has bizarre, jumbled terrain suggesting it was torn apart and reassembled by tidal forces. And some, possibly, could harbor subsurface oceans. Liquid water, kept warm by tidal heating, beneath kilometers of ice. The mission was originally planned for a 2031 launch, arrival in 2044. But in 2023, NASA announced a delay. There's a shortage of plutonium-238, the isotope used in radioisotope thermoelectric generators, RTGs, that power deep space missions. Solar panels don't work at Uranus. The sun is too faint. You need nuclear power, and we're running out. So now, the launch is pushed back to the mid to late 2030s. Arrival in the 2050s. If everything goes well, if funding holds, if the mission doesn't get canceled. But even if it launches tomorrow, the people who designed it will be retired by the time it arrives. The scientists who wrote the proposal will be old or gone. That's the timescale we're dealing with. Decades, entire careers, entire lifetimes. Here's the part that really unsettles me. We've known Uranus exists since 1781. William Herschel discovered it with a homemade telescope from his backyard in Bath, England, 245 years ago. We've studied it with the best telescopes humanity can build. Hubble, Spitzer, Keck, James Webb. We've sent one spacecraft to visit it. Once, for 6 hours. And after all that, we still don't understand it. We don't know why it's tilted on its side. We don't know why it's so cold. We don't know what's happening in its core, or why the magnetic field is so chaotic, or why the atmosphere is cooling, or whether the moons have oceans, or how the ring system formed, or what happens during the 42-year night. We don't know. And here's the thing, Uranus isn't special. It's not an outlier. Exoplanet surveys have found thousands of planets orbiting other stars. And the most common type, are ice giants. Worlds between Earth and Neptune in size, with thick hydrogen-helium atmospheres and icy cores. They're everywhere. Tens of billions of them in our galaxy alone. And we don't understand them, because we don't understand Uranus. It's the closest example we have. The best laboratory. And it's still too far, too strange, too hostile for us to truly comprehend. So let's come back to the observation deck. Back to that moment when you're standing there, hand against the glass, looking at that pale blue-green sphere. You know now what's waiting down there. The crushing pressure, the metallic hydrogen ocean, the chaotic magnetic field, the migrating radiation belts, the cold, the isolation. You know that if you descend, you won't come back. Not because the engineering is impossible, though it nearly is, but because the universe itself conspires against you. Distance, pressure, radiation, time. But here's the question. Would you still go? Knowing you won't return, knowing you'll die down there, in the darkness, crushed by forces you can barely measure, let alone survive. Would you still go? Because someone, eventually, will. The Uranus orbiter and probe will launch. It will arrive. It will deploy a probe into the atmosphere, and that probe will descend until the pressure crushes it. And we'll watch the data stream back, in real time, 2 hours and 40 minutes delayed, as the probe falls deeper, deeper, until the signal cuts out. And we'll learn. We'll finally understand what's happening in those depths, what the magnetic field is doing, what the core is made of, why the planet is tilted. But the probe won't come back. It can't. And if we ever send humans, and that's a big if, a hypothetical so distant it barely seems real, they won't come back either. Because Uranus isn't just hostile. It's beyond hostile. It's a test of whether human ambition can override human survival instinct. And that's the real reason anyone who goes to Uranus will never come back. Not because the technology isn't there, but because some distances, some environments, some places in the universe are meant to be final. I hope this gave you a new perspective on Uranus. If you enjoyed this, consider subscribing. I'll see you in the next one.